that a question? All right, so here's kind of the game plan for the rest. I promised you that I would go over quiz, whichever the last one was. And I will, but it may not be until tomorrow. I don't think the single value, I will get the new stuff behind it. So we talk about and I'm probably going to give you a short quiz, a last quiz, and talk about this that I'll probably post this afternoon, this evening. Single value decomposition. Well, recall, yeah, we have diagonal length curve. Yes, diagonal island. So if we have a matrix I call diagonal, it's got to be square and vertical, right? Got to be square. And there it is. Vertical. This is one of the big things we learn. If you have a matrix that happens to be diagonalizable, then you can write it this way for some controllable matrix. Right? And if a symmetric you might remember. If now we add a little bit of extra oomph to it. If A happens to be symmetric, we can now choose P to be whatever it is. So if A is symmetric, we can actually choose this to be the P to be orthogonal, and we call such a matrix orthogonally diagonalizable, and this is symmetric matrix in statistical. But this falls short a little bit. There are some matrices like this one. That one happens to be not diagonalizable at all. You cannot diagonalize matrix. Check it. This is 2 by 2. You can either try to figure out the eigenvalues and eigenvector to do it, or you can just get on your bulldozer and put the matrices in. Right? And number 2, here's another shortcoming. All this works only for square matrices, right? I don't have a hope of doing anything for matrices that aren't square in particles. Singular value decomposition gets us beyond both problems, right? So the idea is we will be able to write A, we want to be able to decompose any matrix A, no matter what the shape of, as where, let me tell you what these parts are. This is going to be special form M by N matrix. this is going to be sort of the analog of a diagonal matrix, right? So over here in the old days, my special form was a diagonal. This is going to be sort of as close as I can get to diagonal when it not being a square matrix. This becomes a special form. This is m by m orthogonal. And this is n by n. You might say, well, Jim, if it's orthogonal already, why do you write V transpose? Because in our computations, this is the transpose of a matrix that naturally divides. And why is it called singular value? Well, so let's kind of show how we go about this. So I'm not going to prove some detail or anything like that. I might outline a couple things. I'm going to show you kind of where this comes from and then how to actually do it. So we'll start out taking a m by n matrix, any matrix in the world, no matter what the shape. Now, this is a very important observation. We brought this up earlier, and you might not have noticed at the time. Remember, even back in the old days, it's not true that every matrix was diagonalizable, right? Even square matrices like this may still be diagonalizable. Well, let's check out this matrix here. Start with A, and now I am going to take AT times A. Now, there's a number of things that are kind of interesting about just making this. Take A and associate this matrix with it. Well, this one is m by n. What's the size of this one? What's the size of AT times A? It's square, isn't it? It's n by n, because this one is n by m, and this one is still m by n. So this is m by n. So all of a sudden, I've taken my matrix that can look very silly, and I've turned it into a square matrix. And this matrix is diagonalizable. That square matrix. Anybody tell me why? So not only, I mean, this is like totally on steroids here. I've taken a random matrix and I multiply AT times A, and not only I've got this ugly matrix into a square matrix, and now I claim the square matrix, not just that, it can never look like this. It's diagonalizable. Anybody see why? In fact, I'll give you a hint. It's orthogonally diagonalizable. Not as it's diagonalizable, it's orthogonally diagonalizable. Because look at the transpose of ATA. This is AT and AT. This matrix is symmetric. And any symmetric matrix is orthogonally diagonalizable. So I've started with a random matrix, and now I've got a new matrix. Not only is it square, not only is it diagonalizable, but it's orthogonally diagonalizable. And you know what? It's even better than that. It's even better than that. ATA is symmetric, and so it is not only is it diagonalizable, it's orthogonally, which means n linearly independent eigenvectors. You need that to happen for any matrix to be diagonalized, right? You need n linearly independent. So this matrix has n linearly independent eigenvectors, and we'll call them something. B1, B2, Bn, and it's got eigenvalues. Lambda 1, lambda 2. Now, a word of caution here, these are n linearly independent eigenvectors, right? So they're all different. I do not claim that the eigenvalues are different. Some of them may be the same. That's okay. Now, in the situation that we've created here, not only is it orthogonally diagonalizable, not only does it have all real eigenvalues, but in fact, the eigenvalues for this matrix have to all be positive. By the way, let me ask you this. Can anybody give me just kind of an aside here? If you have a symmetric matrix, some random symmetric matrix, do all its eigenvalues have to be positive? I know they have to be real, but they have to be positive. They do not. Can you give me a quick example? That a symmetric matrix? Sure it is. What are the eigenvalues? The eigenvalues, since it's never triangular matrix, all you have to do is read the diagonal. The eigenvalues are 1 and -2, right? So symmetric matrices do not have to have, they have to have real eigenvalues, but not necessarily positive ones. This one, when you build it this way, the eigenvalues are all, I shouldn't say positive, they're not negative. They're greater than or equal to 0. This one we should probably look at. So suppose, let's consider A, B, I. And we'll say that the eigenvector BI corresponds to the eigenvalue lambda I. Well, what is this? This is A, B, I. Notice this is a vector. And how do you get the dot product of the vector with itself? You take the vector transpose times the vector itself. Now let's keep this out. This is B I P A P A B I. But this is matrix ATA times BI. This is lambda I. Because BI is an eigenvector in this matrix. So matrix times BI is lambda. So this is now I can rearrange this a little bit, put that lambda out front. What's another name for this? This is just, this is really dot product of V with itself, isn't it? So this is the length of BI squared. So if you put together all the crap we've done, what did we do? We started with the length of ABI squared, and at the end of the day, we get lambda I into BI squared. Notice this quantity was let me not say positive, but greater than or equal to 0. This quantity actually is positive. And so there's no way this is negative, right? This has to be at least 0. And if this is not 0, it's positive. So the conclusion that you have is so each eigenvalue, lambda I of A is greater than or equal to 0. So from now on, we will assume and it's important just to kind of keep the notation of it, so we're all talking about the same thing. But lambda 1 is greater than or equal to lambda 2 is greater than or equal to. So now we will assume that that I'm going to order the eigenvalues in decreasing order, right? Because I know that they're all at least 0. I'm going to order these in order, and I am going to define eigenvalues, lambda 1, lambda 2, lambda n, A are all non-negative. And we define the singular values notice that you might wonder why I'm going to take the square root of this. Why do we do this? Because really what you're doing is you've got kind of two pieces of A. A itself might be a messy matrix, might not even be square. ATA now has all these nice properties. But what I sacrifice in doing that is basically I sort of multiply A by itself, right? We define singular values. So that, after all, these eigenvalues are eigenvalues not of A. I mean, A doesn't have an eigenvalue of 0 at all. They're the eigenvalue of this. So we define the singular values of A to be lambda 1, lambda 2, whatever that's whatever sigma, sigma n with sigma I square root. Notice that since these are all greater than or equal to 0, I take the square root of them. I'm entertaining the square root of a negative number. So these are called the square roots of the eigenvalues of this, or what we call the singular values. And they will be instrumental in doing this decomposition that I promised. So let me give you this theorem here. So we'll start with an n by n matrix. If B1, B2, Bn is an orthonormal basis for Rn, consisting of eigenvectors of ATA. Okay, so we know that ATA is symmetric, so we know it has n linearly independent eigenvectors. So these n linearly independent eigenvectors actually make actually they make an orthogonal basis, but I want it to be orthonormal. But that's cool because these are automatically orthogonal, and I can just make them orthonormal just by dividing out by the length of each other. And suppose that lambda 1, lambda 2, lambda r are all the constant eigenvalues. Of course, ATA might have a bunch of eigenvalues being 0. We're pulling them all out. So we're only considering these ones right here. Then AB1, AB2, ABR, these are of course the eigenvectors corresponding to positive eigenvalues. Actually, I don't. I'll be working on it later. On the basis. Okay. And rank of A. And this is the theorem that allows us to do the singular value decomposition. So I'm going to give the theorem that kind of lays it out there as far as what the pieces parts are, and then I'm going to show you how to work it out. Yes.
That's supposed to be dead one follow
Where are we talking about that?
at the very bottom. That's supposed to be dead hallway. Or not.
Yeah, dim color is the same thing. Right. So yeah, the rank of a matrix is the dimension of its column. So here's the big theorem. This is so you see me write SVD, very lazy when running a single value decomposition. Let A be an n by n matrix, and rank A, number of linearly independent columns, is equal to R. Then there is a matrix called sigma. the sigma is of the same, it's of the same size as the root of A. So here's the deal. A is an n by n, so it's in rows and columns. This sigma is also an n by n column. What I'm going to do up here, this piece in the upper left is an R by R being the rank of the makers. So it's the same thing as the number of non-zero singular values. So that's a diagonal matrix. And what do I mean by the rest of the zeros? What I mean is R might be less than M or N, right? And so basically what I do is I put this diagonal matrix in here, it's R by R, and I fill the rest up with zeros just to make it of this size, right? So everything I don't know, I fill in with zeros. With diagonal entries, P, the non-singular. The non-zero singular values. Okay. Sigma 1. Sigma R. Then so R make U and R N by N, P and R N by N, both orthogonal. Such that A is U sigma P. So this piece is N by M orthogonal. This piece is N by N orthogonal. And this piece is M by N. And it's that form plane there. With the diagonal entries in that D part being single values of A. Now, I'm not moving here, but I'm going to sketch out how this comes. And then I want to sort of show you how the process works. And then we're going to do a couple of examples. Okay, any questions? Let me show you how you. So here's an outline through. And it's going to be far from complete because all I'm going to do is I'm going to show you some things that you can verify yourself. Then I'm going to actually do some numerical examples. by the previous theorem, you know this in the last bit, vectors here, AV1 with the AVR, form a orthogonal basis for this. It's easy to compute that AVI is equal to sigma I. UI. And so we want this to actually be, we want the use to be an orthogonal matrix. So we define the UIs, the 1 over sigma I API. And of course, you see right here, this part of the formula, this is why you want to do non-zero singular value, because you're totally hosed, aren't you? This is zero. So you only want to consider the signals. Single value. And of course, it's a very natural question to say, and of course, you form the matrix U. With the columns this way. But it's very natural to ask, what happens? You see, U is supposed to be an M by M matrix, right? Well, it's very natural to say, well, what happens if R is less than M? Because now we've only got R columns and I need to have M columns. Then you put in these extras. And this is you expand the first or the normal vectors U1 to UR to a basis U1 UR UM if necessary. So if you've already got in columns, you're good to go. If you need more columns, then all you do is expand this. You've got R vectors in space. Expand this to whatever else you need, and make that a larger orthonormal basis. And B, this part is actually used to orthogonally diagonalize ATX. That is to say, more precisely, the I don't have to worry about completing this one actually, because this is an N by N matrix and it's symmetric, so I know I can orthogonally diagonalize. So this is like an old problem. So take whatever this matrix is, find the matrix you need to orthogonally diagonalize it, and that is V. Take its transpose, use it in this step right here. And this is formed just by taking the singular value. So now I told you how to do everything. And by the way, if you do this computation, you'll see that you can actually easily show that actually AB is U times sigma. Okay, let's do it. Got a couple things to put down here. Let's try this one first. Let's take A, the matrix 1, 0, 1, minus 1, 1. So I'm gonna go through the process, give you the meeting, and we'll show it. Okay. The first thing I need to do is figure out all the singular values. Once I have the singular values, I've got most of the stuff done. So this is, of course, a 2 row by 3, 2 by 3 matrix. And so I need to fix this up myself. This is the little piece that I use to make this square matrix. So AT is and times A. And of course, this needs to turn out to be a symmetric matrix. So this is a good gut check at this point. It should be, of course, a 3 by 4. So this turns out to be 2 minus 1, 0, minus 1, and 0, 1, 2. How about that? Symmetric matrix. Do I agree with that? That's a good sign. Now, to get the singular values, what I need to do is find the eigenvectors and eigenvalues. I will record that over there. Let's do computation here. Again, it's another good gut check to make sure that what you get are all they all better be positive or non-negative energies. Minus 1, 1, x, 0, 1. Good. Okay, so let's see what polynomial is out of this. Let's take the determinant of this, and I get 2 minus x times, see, x squared minus 3x plus 2 minus 1. Then it's going to be minus minus, so it's plus. Let's see, part of these two is x minus 2. Part of these two is 0. And I only got a 0, so that's lucky. Notice I can pull a 2 minus x out of this. Leaving me with x squared minus 3x plus 1. And when I pull 2 minus x out of this, I get minus 1. Again, it's what it is. Ones cancel, and I get 2 minus x. X squared minus 3x. So I get x minus x minus. So I get 3 different eigenvalues for this. So let's start recording this stuff. Three eigenvalues, right? Then equals 0, 2, and 3. Okay, now I need an eigenvector for each of them. I know since I got 3 different ones, then I'll go these 2 in. But what's another gut check? What should be true of these eigenvectors that I get? It should be orthogonal as well, right? Because since I've got 3 different ones, they should all be orthogonal. If I had a double eigenvalue, if I had like 0, 2, 2, it's possible that the 2 eigenvectors that I get for that are not orthogonal to each other. But I can fix that, right? Because I can use Granny Schmidt to make them orthogonal. Yes.
So there are eigenvectors are orthogonal that make this symmetric, right?
Yeah, that's right. Eigenvectors you get for different eigenvalues to be orthogonal automatically. If you have a double or a triple if you have multiple eigenvectors for a single eigenvalue, what you get in the computation may not be orthogonal to each other, but you can use the Gram-Schmidt process to make it so. We had an example like that last time. We got two eigenvalues for one of the eigen, but they weren't orthogonal. We could refine it and make them. So let's go through it. So let's just make this Excel 2 minus 1, 0, minus 1, 1, 1, 0, 1, 2. Okay, so let me kind of do this quickly. I'm going to move this up to the top row with the sign change. I'm going to put this along the right. And I'm going to multiply by 2 and add to that put on the bottom row. So that's going to be 0, 1, 2. Okay, good sign, right? Because that means that this is a singular matrix. It has to be. I'm going to add this to this. 1, 0, 0, 1, 2, 0, 2. Okay with it? And so I'm going to do the eigenvectors fairly quickly because that's the free variable, and this should be minus 2 times this, and this should be this. And it's a quick check that if I multiply this by this, I get 0, 0, 0. There's so I get from the pairs here. Minus 1, minus 2, 1. Okay. Any questions? Let's do language 2. That means I subtract 2 on the diagonal. Like that. Notice, notice the 0, 1, 0 and this, they're multiples of each other. So one of them's row of zeros, and then 0, 1, 0 I'll move to the middle, and they can take out the middle of this, and I can change the sign. Well, 0, 1, 0, bottom. And that's minus 1, 0, 1. Sign on that. So the eigenvector, I get this. That's 0 in the middle. So lambda equals 2. 1, 1. Gut check. Notice the dot product of this one and this one is 0. It's a good sign, right? These two are orthogonal, as they should be. Agree? Now let's look at lambda equals 3. Now I'm subtracting 3 down the diagonal. I'm going to get minus 1, minus 1, 0, minus 1, minus 2, 0, 0, 0, 0, 1,
Why is that on the, why is the first one in the square?
oh, because I lost my mind. You mean right here? Everybody okay with it? Okay. Yeah, thank you for catching me. What would probably happen if I had done this? My guess is if I had made a mistake and worked it out, I would have had 3 pivot columns, and that would have been a mistake. That would have let me know that I had made a mistake. Okay, let's see what happens here. I'm going to go 1, 1, 0. Change the sign of the first one. Comes minus 1 and add this is going to be 0, minus 1, 1, and 0, 1, minus 1. Okay, notice this row and these two are multiple each other. And so I'm going to go 0, 0, 0, 0, 1, minus 1. And then looks like. Okay. And the eigenvector, I get this. That means these two are the same, this is minus. This better be orthogonal to all of them. Minus 1, 1, 1. Orthogonal to this one, and this is 1 minus the same one. Very good. So here I've got 3 orthogonal items. But okay. Now the D part that I need. I need this to be, well, actually, let me build the signal first. Now, the singular values. What are the singular values? Well, the biggest one is radical 3, radical 2, and 0. Right? This is the square roots of the eigenvalues. Now, I throw out 0 because remember I want the non-singular values, and I make sigma this form. Remember what I said, D0, 0. I've got 2 singular values that I can use. So the D part should look like this: radical 3, 0, 0, radical 2. We do the singular values in order of size. That's the diagonal part. Now, that's a 2 by 2 piece of what I need for a 2 by 3 matrix, right? So make it a 2 by 3 by throwing zeros. Simple as that. This is the sigma piece. Let's get the B piece. The B is the vector that I use to diagonalize my ATA, this one right here. And so we put it in the order that the singular values come in. So I should get 3, 3, 3. Remember, I have to make it an orthogonal matrix. And then for 2, I get 1 over radical 2, 0, 1 over radical 2. And finally, the 0 singular value, the length of that's radical 6. Yes.
So you need not to use lambda equal 0 because it's not greater than 0.
What's that?
You didn't use lambda equal 0 because it's not greater than 0.
Well, because remember what we get for our U vectors, you have to divide by the sigma, and you can't divide by 0. And so the zeros are kind of taken care of in the process. Notice the transpose of B is also the inverse of B. Okay, so I've almost got the decomposition because I've got this part and I've got VP. Right? The only other part I need is I need the 2 by 2 matrix U. And fortunately, I don't have to expand it to a basis. But U1 is 1 over sigma 1 B1. Oops. And AB1, so in this case, it's 1 over radical 3 times the matrix 2 minus 1, 0, minus 1, 1, 1, 0, 1, 2. comes V1, which is minus 1 over radical 3. 1 over radical 3. 1 over radical 3. So notice it's just the first column. It's the one that corresponds to the radical 3. So this is 1 over radical 3 times, this is going to be minus 2 over radical 3, minus 3 over radical 3, and 0. So this is actually going to be right. So this is minus 2 over radical 3 minus 3 over radical. It's a oh, I put AAT. So this is 1, 0, 1 minus 1, 1 times the vector minus 1 over radical 3, 1 over radical 3, 3. And this is, that's going to be 0. And this is going to be 1, 2. That's going to be 3 over radical 3. So you actually just 0, 1. And for U2, this is 1 over radical 2 times one over radical 2, 0 minus 1 over radical 2. In this case, I get the vector. That's going to be this is going to be 2 over radical 2, so that's going to be 1 here and 0 here. And so U actually, rate U should be actually. You might ask what happens if you do U3 times this. Since I got 0 as the third singular value, you'll actually get the 0 back. So there's your U, there's your V transpose, and there's your sigma. And you should check if this works out. Any questions? We'll talk more about this and go over the quiz. Bring questions on Friday as well. Any questions on this?